In this video, we solve problem 3 of Unit 15. In this problem, we have 4 wires, long parallel wires that are all perpendicular to the screen. Wires A and B have a current that is going out of the screen, so that's why they have a point. While wires C and D are going into the screen, so they have a cross, though it's difficult to see. So I'm going to put it more clear like this. So this is, these are points, okay? So they ask us, they all have the same intensity, so the same electric current. So the intensity, the electric current in A, it's the same as in B, it's the same as in C, and the same as in D. This is 5 ampere. And they are asking us to find the magnetic field at the middle of this square when we know that the length of the square is 0.2 meters. So we know that when we have a wire, if we look at it from above, we know that if the current is going out of the screen, using our right hand, we can remember what is going to be the direction of the magnetic field around the wire. And to know it, we just have to put our thumb in the same direction as the wire, as the current in the wire, and this leaves our fingers going around in this direction. So the magnetic field is going to have these field lines. So at this point, magnetic field is like this, in this point like this, etc. Okay, and we know that the magnetic field, the modulus, is going to be equal to mu sub 0 divided by 2 pi times the current divided by the distance at each point. We call it normally r. Okay, so in this case, as all points have the same, all currents have the same distance to the point P, they're all going to have the same modulus of the magnetic field. It's going to be BA is going to be equal to BB, this one to C, and this one to D. And we can calculate it easily if we know R. Okay, so to know R, we know that we use just geometry, and with geometry you know that this is 45 degrees. Okay, this is 45 degrees, so we can calculate this distance R, and it's going to be equal to 0.2 divided by 2, which is this length here, okay, times 1 divided by the cosine or the sine of 45 degrees, which is this here. So we know that this R in all cases is 0.14 meters, okay? So we just calculate, I'm going to call this directly B. So we calculate B, and it's going to be just mu sub 0 divided by 2 pi times 5 ampere divided by R, which is 0.14 meters. And we know that mu sub 0 is 4 pi 10 to the minus 7 Tesla times meter divided by ampere. So if you do this, this is going to give you 7.1 times 10 to the minus 6 Tesla. Okay, so now we just have to discuss the directions and see, because you have to remember that the magnetic field is a vector, so we just have to be careful adding up the vectors. Okay, so in the case of the wire A, if we apply the right-hand rule, we can see that the magnetic field has to have a direction that is just perpendicular to this line here, because it has to go with a circumference of with center on the, it has to be tangent to the circumference that it has center in A at this point P. Okay, so this has to be perpendicular to the radius. So this would be the direction of B sub A. Okay, for B sub D, if we get into D, D, remember that is going into the screen. So if we do the same, we use again our right hand, we will see that BD has also the same direction. Okay, so BA and BD have both the same direction using your right hand. Okay. And then for the wire B, if we use our right hand, then the direction is going to be just this here. This is going to be BB, because it has to be a tangent to a circumference that has center in B and at point P. So this is going to have just this direction here, okay? And if you do the same with C, you place your finger pointing into the screen, then you will realize that the magnetic field of B and of C, are also the same. Okay? So we just have now to put it down into coordinates, and really you can already see that as they have the same modulus, but and the same components x and y, they're going to cancel out the components on x, and you're also only going to have components on y. So I'm going to place there the y-axis and here the x-axis, and they're going to compensate. So for BA, which is equal to BD, as the angles are 45 degrees, it's easy to see that these two have to be equal to the modulus times this for I and this for J, okay? Because they both have a positive sense. So we just have to remember that if this is X and this is Y, and this was BA or BD, and this is 45 degrees. That's why here is the cosine of 45, this is the cosine of 45 degrees, and this is the sine of 45 degrees, okay? On the other hand, BB was equal to BC, okay, which is B times, and here what we have, if this is X and this is Y, what we have is just the contrary. So this is BB, and 45 degrees is this here. So this has to be minus square root 2 divided by 2, which is in the I, using the I, unity vector, and this is square root 2 divided by 2j. Okay, so this is again cosine, the cosine of 45, the minus cosine of 45, and this is the sine of 45. Okay, so when we add them all together, the total field at point B, which is BA plus BB plus BC plus BD, all added up as vectors, is like 4 times one of the components in the y-axis. Okay, so it's just 2 square root of 2 times Bj, okay, which if you do the calculations is 2 times 10 to the minus 5 Tesla in the j direction, okay.